Good afternoon, ladies and gentlemen. My name is Christoph. I'm representing Prose. Prose is a designing and engineering company, and we provide technology transfer abroad of Switzerland. But first of all, I would like to thank the responsible people who made possible this conference and who have invited me and gave me the opportunity to present this paper. And I also would like to thank you, ladies and gentlemen, for taking your time to listen to this presentation. As I said, Prose is a designing and an engineering company, and I think we are obliged to give some technical details about components, in our case about wheels and wheel sets. First of all, let me show you the content of my presentation. Equivalent conicity. Then I give you some information about wheel wear at high speeds. Then I talk about instability. Then I talk about the advantages of individually rotating wheels. Then I make a comparison with conventional wheel sets. Then I give you also information about the advantages of mechatronic elements. Then I make some commercial considerations, and finally I come to the conclusions. So, a characteristic value of the wheel rail interaction is the so-called equivalent conicity. On the right side of my slide, you see this characteristic movement of a wheel set. So it's synodal movement. And that produces a rolling radius difference at a certain lateral amplitude movement of the wheel set. And this can be linearized, and the characteristic value is the equivalent conicity. This equivalent conicity grows during the lifetime, and at high equivalent conicity, the bogie has a hunting problem, or the whole train has a hunting problem. The TSI, the technical specification of interoperability, requires for vehicles with a speed above 300 kilometers of an equivalent conicity smaller than 0.1. That's before the wheel starts to wear. Now, what we have seen or observed in the high-speed railways is a wear pattern. This wear pattern is characteristic for high speeds, and it's located around the tape circle, so in the middle of the thread. These high-speed tracks are very well aligned, and the curve radius are rather large. That means you don't have a lot of lateral movements, these lateral amplitudes. Since you have a very good track, means your rail imperfection is very, very small. So, yeah. I can magnify that. Here you see the magnified view of the wheel wear. The blue thing is the original thread, and the red thing is the worn profile. So now this wear pattern has an impact on the equivalent conicity. For very small amplitudes, you see a high equivalent conicity. Here on the x-axis you have the lateral displacement, and here you have the equivalent conicity. And you see here at the amplitude of 1.5 millimeter, the equivalent conicity reaches a peak. sorry. And then it goes down with the increasement of the amplitude and is stable at 0.3. So these small amplitudes produces these peaks. Now the question is, how does the equivalent conicity evolve during the accumulated running distance? As mentioned before, the TSI requires 0.1 at the beginning, at a new profile, and then the train starts running, and you see on the x-axis, that it goes up to 300,000 kilometers. And above 250,000 kilometers, the equivalent conicity starts to increase. These are figures which we have from high-speed operation. So, and to keep this equivalent conicity, you only have one option: you have to reprofile your wheel. So, now how can we control the vehicle stability? First of all, there are two forms of running instability. There is the boogie hunting. I show that. So the boogie hunting means the coach remains straight in line with the track, and the boogie makes lateral movements and rotational movements. This happens typically at high equivalent conicities and has a high frequency. This hunting movement is safety critical because it produces high forces on the track and on the wheel set, and it affects the ride comfort. And then you have the second vehicle instability. In this case, the bogies remain straight and the vehicle body makes a movement. That occurs at low equivalent conicities and has a very low frequency. It is not safety critical, but it deteriorates the ride comfort. So now what are the classical means to prevent this running instability? You can stiffen your axle guides. So you introduce, for instance, a rubber element with a high stiffness, and you choose high yaw damper stiffnesses. That has a positive influence on the stability at high conicity, but has the tendency that at low conicity the vehicle starts hunting. And it's adverse to the forces between rail and wheel in curves, so it increases these forces. Then you have the second option: you lower your axle guide stiffness and you lower your damper stiffness. That increases the behavior at low conicity, and behaviors increases the behavior in curves. You have a better wheel steering, but it decreases the stability at high conicity. So you can say you have a very, very small range in which you can optimize your stiffnesses. So during the lifetime, the conicity shall be kept in very small bounds, since you have no means to influence the behavior by these stiffnesses. So now what is this theoretical solution? You can go to individually rotating wheels. Since they are individual, the rolling radius difference has no influence, and there is no equivalent conicity. This feature reduces the self-steering, which is known, and the steering property in general. That means your bogie could shift sideways and remains in this position and never goes back to the center of the track. But there is another disadvantage. When you're running through a curve, then there occur friction forces in the thread. And a wheel set is a very stable and rigid component and can maintain the wheel distance very easily. So if you have individual wheels, you have to integrate other elements which maintain this wheel distance. We have heard in the presentation that Talgo has such running gears to control these shortcomings which I have mentioned before. Now, what can we do to optimize the parameter of conventional wheel sets? We could integrate hydraulic axle lever bearings so they adapt, or the stiffness is changed. On a straight track you have a high stiffness, and in curves you have a lower stiffness. You could use innovative yaw damper designs. I will come back later to that. Or in general, you could reduce the weight of your unsuspended components, or you even could put your motor to the car body rather than have it in the running gear. All this reduces the masses and consequently the forces. Now you have a further option to prevent the instability. You have to maintain a very good profile. The traditional way is you reprofile your wheel at a certain maximum maintenance interval. That has the disadvantage that you have to remove a considerable amount of material, and that's expensive. The other option is you remove frequently less material. This means you recondition your wheel profile very early, and that leads not to a very bad wear pattern. Now our proposal, which goes beyond this traditional measure, is to introduce mechatronic elements. And the aim is to improve these lateral dynamics. So there could be active steering be used to control the wheel wear. That means you steer your wheel set in a way that it doesn't remain in this middle position of the thread, so it wears evenly. And that could be done continuously. Another thing is, because the wheels are decoupled, there is no connection between the left and right wheel, you could electronically couple them and influence the rotation, and you could have an artificial centering or synodal running of the wheel set. And the last one is you could read your dynamic behavior when running and changing the parameters of your axle guides or dampers in order to maintain a stable, a good behavior of the running. So there is one big question: what's the safety of such a mechatronic element? It's very clear that such a system must be safe when the mechatronic element is faulty. So the solution is that in case the mechatronic element is faulty, you fall back to a passive safety state. So in this state, maybe the wear is large, but the boogie is running safely. And in a daily inspection, you could replace the faulty mechatronic element, and so you don't allow to increase the wear. So some commercial consideration. It's quite obvious that mechatronic elements are costly, so the investment costs are obviously higher than for a classical boogie. But since you have to keep your equivalent conicity in a very small span, you have to maintain your wheel frequently and your rail. So the life cycle cost could be higher due to this maintenance cost. So for ultra high speed application, we think these new concepts could be a viable solution. The alternative is to optimize the traditional components. So my conclusion is the equivalent conicity and rail profile combination have a significant impact of the running behavior. Wheel wear is difficult to control for high-speed vehicles, since the networks have dominantly straight tracks sections. A transition to an individually rotating wheel can reduce the influence of equivalent conicity. And as mentioned before, these mechatronic elements could be a viable solution. Thank you very much.